Hello world. So it's been a little while. I slowed down the posting of questions, so we do 2 a week instead of 5 a week, um, which is still a good amount, I suppose. Um, let's see what I can show you. Yeah, there you go. All right, this is not the current problem. This is today's problem. Um, I'll do this one last, but we've got about 6 to do. So we've got this calculus problem. A lot of these will sell you in the title, give you a pretty big hint what it is. Um, we've got a multivariable problem about arc length. We have got differential equations. So this is probably the first time we're seeing like an ODE. Let's see. Well, I guess not the first time, but it's the first kind of challenging one. The rest of these, this one is a separable. And then after that, last week was like an applied. This is just an algorithm. You're constructing these points by a specific algorithm. But this is the first one where I could see if you don't know the method, this is pretty tough. Anyway, then we got 3 more. We got linear algebra, Lontief input-output analysis. Really, I think the whole challenge is knowing this formula. So this equation is given to you. So if you're comfortable working with matrices a little bit, you can probably solve this one. So there is some specific stuff that you do, but it's all just dictated by this concept. So we'll talk about that in a minute. And then abstract algebra. These ones are starting to get a little trickier. This is a question about cyclic groups. And then the last one, real analysis. These are also a little tricky. A couple of them I think are pretty straightforward, but a couple are a little more challenging. So we get started. Let's look at this calc question. So this is 44. They want the sort of general antiderivative of this function. Root 16 minus x squared, all of that divided by x squared dx. Sometimes it's trickier, but usually there's a couple of trig identities you want to keep in mind when you're doing these. Tangent square, you have to know your integrals and derivatives of the most common stuff of like the trig functions. But besides the obvious sine squared plus cosine squared equal to 1, you also want to know that this is true. So the reason is this is sine squared over cosine squared. So 1 is cosine squared over cosine squared. So in your numerator there, you're getting 1 over cosine squared. So this immediately happens because of sine square plus cosine square equal to 1, that identity. But what does it have to do with this? Well, if I had a form that involved, if I was taking an integral and it involved something like that, I would know to try tangent as my substitution. I would let x be tangent and see where it goes from there. Take the derivative. So d dx, or dx here would be secant squared of theta. And then, we plug it in, substitute for any x's if you have to, and see where it goes. It's funny, I said that. So then I was about to be like, what about 1 minus x squared, right? Which is kind of what we have. So on the other hand, let's continue my train of thought here. If we had x squared minus 1, That's a lot like this same identity, but you just subtracted 1, right? And you're getting tangent squared. So it looks like you're looking at tangent squared, whereas here it looked like you were looking at secant squared, right? If you do the substitution, this becomes secant squared. In this case, this new case I just dreamed up, if I subtract 1, you get an identity that looks a lot like this. Your intuition should be, I'm going to let x be secant. And then this is clearly secant squared minus 1. So this left-hand side becomes tangent squared, right? We're not actually in either one of those situations, which tells me we're in the other case. If we had looked just directly at sine squared plus cos squared equals 1, right? That's what I think of when I have this kind of form, which is similar to what we're looking at here, right? When I have this form, I want to let x be sine, so that 1 minus sine squared gives you back cosine squared. So that's my instinct on this type of problem. I'm gonna let x be 4 sine and see what happens. Because we're squaring the 4, you'll get 16 in both terms. You can factor the 16 out. Well, square root of 16 out. And then downstairs, I guess we get an extra 16. We get a sine squared. So it's unclear what's going to happen. But it doesn't just go away. We have to also replace, everywhere we see an x, we either substitute it with effectively cosine squared or sine squared. So if you see an x on its own, it has to be replaced with this 4 sine theta. Before we do that, though, let's address how we're going to replace the dx. We're going to get 4 cos. That's sort of shorthand for what we're doing. So that's how we're going to replace, like basically you replace it with d theta, but an extra cosine theta pops out, an extra 4 cosine theta. So this integral, by this substitution, this integral is equivalent to, or equal to actually, we're going to have, let's do it kind of slowly, 16 minus 16 sine squared. Downstairs we get x squared, which is 16 sine squared. And then dx becomes this 4 cosine. That's outside of the radical sign. So that looks worse at the moment, but that's the same integral in a different space. And all this came from, I thought of doing this substitution because I'm familiar with this form, 1 minus x squared. Anyway, it's pretty gory, huh? So you can factor the 16 out. You'll get root 16 is 4, 4 times 4. So the 16s actually cancel. And we're looking at the square root of 1 minus sine squared, all right, which is cosine. Does that make sense? Like by this identity, cos squared is 1 minus sine squared. So if you just took a square root on both sides. So I have 1 minus sine squared. We're taking the square root. It's going to become cosine. So upstairs you have cosine squared, and downstairs you have sine squared. And the 16's canceled. So we're now looking at that, which does look nicer. It's cotan squared. Which I don't remember off the top of my head. So you know what we're going to do instead? I'm going to do another u substitution, I believe. Huh. Doesn't quite work, does it? If you let u be sine, you do get cosine, but you don't get cosine squared. So I really need to just be able to do this one. I wonder, no. Yeah, I shouldn't get stuck here. If it was secant, we'd be done immediately, right? We would just integrate. Um, anyway, I'm stopping here because I'm a little rusty and I just don't remember. I haven't done the U substitution because I can see that it's not going to actually work out for me, right? Even if I let U be sine squared, that's weird. But the derivative is 2 sine cosine. It's not this. Yeah, I don't quite remember this at the end here. We could do... you know what we could do is like, this is 1 minus sine squared, right? So if I knew how to integrate cosecant squared, then we'd be pretty much done with this problem. This first part is cosecant squared minus 1. I don't know that off the top of my head, but my instinct would be, since the derivative of tangent is secant squared, this is probably cotan, or maybe like negative cotan. So let's check that out. If we differentiated cotan, right, with a quotient rule, you'll get the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. That's negative 1 over sine squared. Which is cosecant. Yeah, it's the negative. So I have it backwards. Well, it's supposed to be a negative sign there is all, okay? So we're getting that the derivative of cotan is negative cosecant squared, okay? So, yes, it's cotan squared, but you know, that doesn't really help us. You want to write this as 1 minus sine squared using that identity again. And then your integral is now the integral of cosecant squared, which we now know what it is. It's the negative of cotan, minus 1. So we're getting negative cotan theta minus theta plus c. And if you're lazy, that's not wrong, but you should really put it back in terms of x. You know, so now I need to figure out what cotan theta is in terms of x and try to put it back. The way you do that is use this original equation that you came up with, your x substitution. I usually make a little triangle, so like this is saying x divided by 4 equals sine. So I could make a little right triangle, right? And here's our angle. And then sine of this angle would be what, opposite over hypotenuse, so it would be x over 4 like this. And we probably need this length, so I'm going to go solve it using just Pythagorean theorem, right? So this is root 16 minus x squared, which probably looks familiar. So we're there, and then in this picture, cotan of that angle would be not opposite over adjacent, but the other way around, right? So adjacent over opposite. It's like 1 over tangent. So we get this over x, like that. We want that's our first term, the negative of that. And then if you're solving for theta, unfortunately, it's going to involve an inverse trig function. You're not going to have a nice clean thing. You have to have a function there, you know. So you could just do arc sine of x over 4 if you want. It's probably how I'll leave that one, okay? But there's a few things you could write there, right? You could do inverse tan of x over, the reciprocal of this. However you want to solve for theta, but it's going to involve an inverse trig function, unfortunately. So our final step is to put all this stuff back in terms of x. Cotan is this stuff, so I get negative root junk over x, like that. That's the first term. And then minus theta, but theta I'm saying is some inverse trig function. So I'm going to go arc sine or inverse sine of x over 4. And that is our final answer on this one. Yeah. So let's see what's next. This multivariable problem about arc length. So 45. I mean, I could just spit out the answer for you, but when you have, I guess I haven't thought about this recently in like multiple dimensions, but where this is coming from is that if you're at a point that's differentiable, you can, like here, we'll look at the one variable case. So here's our function f of t, or at some location t. Suppose you want the arc length from like A to B, right? And we're at some location, say t. Well, we're at a number of locations between A and B, but my point is going to be that you're trying to, you're sort of summing up. One way to think about this is to sum up all these small chunks. Take little steps of size, say delta t, and this height we can approximate using a derivative. We can then use both of these values, these little deltas. Let's call this delta y, for instance. You could just use Pythagorean theorem, of course, to get this length, right? This is going to be a square root of delta t squared plus delta y squared. So that's where the arc length formula is coming from. It's the sum over various t's, like let's say the sum over, let's call it I suppose, less than I, less than n, where you let delta t be the length of the interval cut into n pieces, and then your y values come from the function evaluated at some point, well, I guess it's actually just not even this, right? This height would be that point plus the derivative times our step size. But then we're going to subtract. So here's the upper y value, okay? I'm just going to continue my thought. Plus the derivative at that location times your step size, right? So there's your second y value right there. And then your first y value, this height comes from the original point, is f of ti. So you're getting just delta y is the derivative at ti times the step size. So this sum is this formula, square root of delta t squared plus delta y squared, but delta y contains delta t. So you're seeing delta t squared there as well. So you're getting, if you want, you could factor delta t out and you'd get 1 plus just this part, f prime of ti squared times delta t. So that's a brief derivation in one variable anyway of where this arc length formula is coming from. This is more like, I guess you see this in Calc 2. I don't know if you really see it in Calc 1. We're actually going to be doing this is Calc 3, so we're actually doing it in 2 dimensions now. So you have sort of a total derivative thing that's like both the x derivative and the y derivative, you know, the derivative in 2 directions. But it's the same principle. And so what we end up with is partial derivatives. A partial here squared plus a partial there squared. I didn't really derive that in 3D for us, but here's a rough sketch of the single variable calculus idea of how to get an arc length. Now you take the limit as n goes to infinity, so this becomes a dt, and this becomes just a continuous variable instead of your discrete set that we were sampling on. So in one variable, you'd get something like this. Okay? Now we're actually using the 3D version, that the arc length will be I want to say, well, let's write it as say we could put fx here, or you know, whatever you want to put. So we'll put fx squared plus fy squared with respect to t. Where so f is a function of x and y, but those are ultimately a function of time, and we're letting time vary from a to b. So we're using this formula. Forget the arc length. So finally, back to our question. They have this vector-valued function. I usually think of that as like a point in space in 3D that's moving around as time changes t. So they've given us r of t is t squared t cubed, right? Over the interval like that. All we need to do is differentiate this function in, yeah, it's kind of funny I phrased it that way. But what I want is del x del t. Yeah, this was a weird way to phrase it. But this function's derivative in the x variable, in a sense, and this function's the derivative in the y variable. So like del r. Well, here, let's just do it this way. R prime is 2t 3t squared, like that. And these are your derivatives that I'm going to be using in our formula. So that's pretty much all we do. We're just now able to say integrate from 0 to 4 square root of this derivative squared plus this derivative squared dt, whatever that works out to be. So we're getting 4t squared plus 9t to the 4 onto the radical. You can factor t squared out, right? Otherwise, this would be a really nasty problem if that didn't happen. It started to make me question whether there was like an extra factor that I missed there until I saw that this happened. So you got to be a little careful, I guess, when you're constructing questions like this. You could easily come up with a function, not that it doesn't have an answer, but you could come up with something that's really kind of a nightmare to integrate. So we want to find 0 to 4 root 4 plus 9t squared t dt, right? If you just do a u substitution, we'll be okay on this one. But you can see why I started to hesitate, because like if I can't do the u substitution, this kind of sucks. It's like similar to a trig integral that we just looked at, but not very nice anyway. 18t dt. So it looks like I can replace this with 1/18th, and then this is root u. I'll have a du here, right? And these numbers have changed. So like when t is 0, u is 4. And when t is 4, you know, u of 4 is like 4 plus 9 by 16. So what's that, like 90 plus 54? So 90 plus 58 is like I want to say 148, right? 9 by 16. 90 plus 45 is 135, plus another 9 is 144, plus 4 is 148. Yeah, I can't do it any more ways. So there we go. Integrate this. You're getting 2/3 u to the 3/2 evaluated from 4 to 148. And then don't forget to multiply that by 1/18 when you're done. Yikes. So at 4, we get 2 cubed is 8. Yeah, I don't know. Guess maybe I'll... Oh my god. Okay, yep, of course. 4, 8. Man. It would help if I knew how to use this calculator. There we go. 148 square root. Why does it do that? Square root. 48. I see. It's like continuously. Sure. Anyway, that's the square root of 148. If we find a way to cube it, we get this pretty big number, 1800 and a half. What is this? 2/18 is like a ninth. So this is 1/27, right? 1/27 of, and then here I seem to have gotten 1800.5 for when you plug 148 in. And if you plug 4 in, you're getting 8. Because the square root of 4 is 2, and then you take 2 cubed is 8. So this is the answer that I get. Getting 66 and 7/18. Getting 66.388 as an arc length for this function from 0 to 4. All right. So that was 45. 46 is a differential equations question. The topic is integrating factors, is what you're going to have here. If you move this term to the side, we're looking at something like y prime minus 4y equals some other function, right? The motivation for the integrating factors technique is that this left-hand side kind of looks like the product rule. If only we could make it look like the product rule, you know? So you imagine that, if you just want the answer, you're doing something like this. This is p. This function is called p of t. Right? So in our case, p of t is -4. But you get this form over here where you've got y prime plus some stuff, right? So we're going to have a function that's just e to the integral of p of t. And that's not the whole story, but that's the function that you're going to end up multiplying by over here. So the idea is we have some mystery function mu that if we multiply it on the left by it, we would almost, it looks like it's the result of a product rule. We can sort of force it to be the result of a product rule as long as this was u prime, right? So then you got mu y prime plus mu prime y, which is the derivative of mu y. So at that point, we could integrate both sides, right? Now that we know the left-hand side, I mean, if we had found this function, right? So that's where this formula is coming from. Most people, when they do these problems, they just recognize it's an integrating factors problem, and they say, okay, this is that function. And then they can basically just spit out an answer at that point. You'd have to do one more step. You're going to integrate this, but we'll see. I'll just derive it. So if on the left-hand side we had this stuff, say we had the derivative of this equals some other function. Let's call it g on the right, okay? Then if we integrate both sides with respect to t, on the left, you're going to get this product. And on the right, we're going to get just whatever that integral is, right? Then you just divide, and you're done. So the answer is this integral. Oh, you know what? I forgot to. When we multiplied by mu, it ended up on the right-hand side as well. So it probably makes a lot more sense right now if I do this, if I put a mu there, okay? So the thing you're integrating on the right involves mu as well. So there's mu there. But when you're done integrating, you also put 1 over, you divide by mu. So there's your answer. The reason I changed it up is that you're probably thinking of this as g, right? But I forgot that I multiplied by mu on the left-hand side. So multiply by mu everywhere. That changes your right-hand side, right? But you have to first find mu, which means you solved this. And this is the solution to that. Now I'm wondering if I feel like I might be missing a negative sign. Is this a negative p? Maybe? Can't quite remember. So if I were solving like mu prime equals up, well, okay, this is just separable, right? You could divide, you'd get log mu is the integral of p. So I guess there is no negative sign there. I wonder why. Let's see how it works out. I don't know why I started to think there was a negative sign. Maybe I'm just remembering it differently because, like, if you stick with this original form, what you're integrating is, of course, the negative of this number. But I moved it to the left, so maybe we have no problem. I mean, it seems we have no problem. So. Yeah, I think we're okay. So anyway, using our numbers, you would usually first find this integrating factor. For us, it's going to be e to the integral of -4, all right, dt like that. So it's e to the -4t. And then you don't really have to, you basically just jump to this step. You could also just quote this, but you still have to do that integral. You don't just stop there. If you wanted to just use this function and plug it into this formula, that's fine. That's correct. So by our formula here, we're going to get 1 over mu, that's this. And then we need to integrate mu against whatever your original function on the right-hand side was. And you can see in this case, it's kind of nice because those cancel out. So you're just getting -5 times whatever the integral of dt is. So it looks like I'm getting -5t e to the 4t as an answer for this one. And I think that's correct, actually. If you Took the derivative of the first, you get this, plus the first times the derivative of the second would give you minus 20t. But if I add this, I get 4y, which is negative 20t. Did that make sense? I think that was the same. I'm just trying to verify that. So I'm saying y prime is derivative of the first times the second. That's that term right there. Plus the first times the derivative of the second is actually a minus 20. Yeah, that's correct. That's correct. And that happens to be 4 times y. Okay? So if you add this to both sides, you're seeing that you are getting the correct answer. So this is the correct general antiderivative for y. We have solved this ODE. Okay? Let us move on to 47. This is a linear algebra thingy. Again, I think the tough part on 47 would be just knowing this formula. Usually when you'd present this stuff, they just give you, like, they give you a big word problem, and you have to know what you're doing enough to remember this formula. Okay, but this is coming from the idea that we want to, like, suppose you had two industries that depended on each other. Like, in order to generate some amount of electricity, you needed some electricity already, and you needed, like, water. And then someone says, oh, I want this many units of electricity. Well, like, we can't just give you 20 units. We need to actually make a little more. Like, we need to provide 22 units if we're going to be left with 20, you know? So the idea is that you have demand here, D, for a couple of products, but it's going to take more than 50 and 30 units to make them. But it's governed by this equation. So what you'll actually need to produce is this amount x, where you have a consumption times x, you know, some of it's used up, plus the demand. And then at the end of the day, you can say, all right, this is how much production will need to be made in order to be left over with D. So I'm not going to, you know, rederive that or anything. That's where the formula is coming from. But we just want to solve for x. So you can do something pretty nice, just subtract. You just do this, which looks like I minus c times x, right? So that's another way of writing the formula, that input-output analysis formula. Then if you want to solve for x, it looks like you could just multiply on the left by this guy's inverse. So we're going to need to find, this is a 2 by 2, we're going to need to take the identity matrix minus our matrix C. Okay? That's 1, 0 minus half, 0 minus 0.6, and then 1 minus 0.2, right? So take the inverse of this and then multiply by D. So, you know, this is the guy we want the inverse of, and then we'll multiply by whatever your demand is. And so if we had a matrix like A, B, C, D, and I want its inverse, you first have to take the determinant. Let's just write it as absolute value of A, okay? And then you did something kind of specific. I want to say you swap the main diagonal and negate the off diagonals. But rather than reprove it to you, I'm sure we've done it before. Yeah, exactly. Swap the main diagonal. You look at the main diagonal, you change the order of those entries, and then you negate the others. And unfortunately, that only works for a 2 by 2, but so you'd be doing something like this, and then you negate the off diagonals. So in our case, our determinant is, let's call this A, okay? Determinant of A is AB minus CD. It's like this minus the product of these two. So half 0.6 is like 0.3. These are canceling. You're still getting a subtraction, so we're getting 0.8 minus 0.3. We're getting 0.5 as the thing that you're dividing by right there. So this inverse, this guy, is 1 over 0.5, or 2 times. And then we're going to swap the main diagonal entries, and we're going to negate the off diagonal entries. We're going to keep them in the same location, but we're going to negate them. So I get this, which if you double everything is 1.6, 1, 2, and then this one's a 1.2. So this is the matrix we want to scale this vector by. So our final answer is 1.61, 1.2, 2 times the demand vector. And so you're getting, the top row is first times first plus second times second. You're getting 50 times 1.6 plus 30 times 1. And downstairs you're getting 50 times 1.2 plus 30 times 2. And the only way I really had to check my work, obviously we could plug it back into this equation, but that's kind of silly, right? Because we just use the equation. But the only thing I can tell you to verify your answer at the end is make sure it's more than the demand, It couldn't be less than the demand. So I know this is going to be more than 50 and then more than 30, but how much more, I'm not really sure. Let's see, a fifth of this is 10, so this is 60 plus 30 times 60 plus 60 is 120. It's a huge amount. But then again, these numbers were kind of big, so I guess that's probably okay. Yeah, that first number being 1. The numbers are kind of big, so that doesn't scare me, I guess. And then 0.6. What's that, like 30? So this is like 80 plus 30. So that's our final answer on this one. Let us move on to 48. So suppose G is cyclic. It's generated by this guy, which means it's, I guess we could start at 1 if you want. Let's start at 1. Anyway, so these are all the powers that you get in the group, right? And since it's telling us it's of order 144, there's 144 of these if you include the 1. So it's going to stop at 143. If you were to get 144 as a power for this generator, it's going to be equal to the identity. That's kind of what they mean there. How many elements would there be in the subgroup generated by x to the 26? So the naive thing, let's look at this with some smaller numbers. The naive thing would be to sit here and start generating x to the 26 is, oh, I didn't mean to put these brackets there, sorry. I just meant to list them. It's not like I was generating a bunch of groups with those items. Yeah, so the naive thing, which you should not probably do here especially, is just start listing them, like here's one, and then if I multiply by itself, I get x to the 52. And then if I cube this, I get x to the, 78? You're going to be here for a long time on this particular example. But that's the idea. They want to know how many are here. How many distinct items do you get? So if you don't already know off the top of your head, it involves the greatest common divisor between like 26 and 44. So let's say, let's call this h, and we'll call this g, and we'll point out that g is this big. And we're trying to find h. But clearly it has something to do with how 26 divides that, right? Something to do with it. I'm not the best at algebra, so I would probably try this and be here all day. But let's look at a smaller example. Like, I mean, some easy ones would be like, suppose you had a cyclic group and its order was 12, right? And then you had, if you look at easy ones like x squared, you can kind of tell there's going to be 6 items there, right? It's going to be x squared, x4, 6, 8, 10, and then the 6th one is the last one, then it starts over again. So here's one cyclic subgroup. You know, it's a subset of G, but it's also a group. I'll go ahead and write x to the 12 there, but of course that's 1. Another easy one is like x to the 6. You get x to the 6, x to the 12. So that's a smaller subgroup. Notice here the greatest common divisor between your order here, or not your order, but this degree and the size of the group that we started with, the greatest common divisor there is itself 2. And 12 over 2 is 6. And here the greatest common divisor between 6 and 12 is the number 6. And again, you're seeing, I mean, I'm kind of jumping to the formula already, but the size here is 12 divided by, these ones were easy examples, right? So they might lead you to think, oh, I'll just divide by, you know, is it just 144 over 26? It worked here because that was what the GCD was basically itself. But if we look at a more interesting example, what can I do? Like 8, maybe? So the greatest common divisor between 8 and 12 would be maybe 4, right? 8 doesn't divide 12, but 4 does. 6 does not divide 8, you know. So this works, though, as a divisor of both. And if we start to write down powers of 8, I mean, I guess you're just going to be observing that I'm right. 16 would be 4 mod 12. And then if you do this again, you get 12. So we're getting 3 items. So you can see that this formula is correct. If I take 12 over 4, we get the right answer. But I thought we might be able to see, you might kind of be able to see why. Because like 8 is, this number 8 is really 4 times 2. So when you take powers of it, Yeah, I didn't do a great job explaining this last bit. I had a better explanation in my head the other day. But the point sort of is, well, I guess I'm saying it contains this greatest common divisor, right? So as soon as you get to an element where you've got your GCD times the divisor, like I don't know what to call it. Let's say K is 12 divided by the GCD that we're talking about. In this case, it's 4. As soon as you hit that K, you're getting a multiple of our order. And so this, at some point, not necessarily the full, well, at some point you get an element that's 1, like you knew that was going to happen, but it happens when the number of steps that you take is equal to the order divided by the GCD. I mean, that's obvious from the formula, but I'm saying it's actually kind of clear if you think about these powers as being multiples of this GCD. Okay, so like in this case, we hit 4 times 3, which is 12. So you knew that this was going to be 1. I mean, it happens to be not 4 times 3, but 4 times 6. But it contains a multiple of 12 because it contains the GCD times this other factor. Okay? Yeah, that was a pretty shabby job of explaining it. But the formula is basically right there. So for our example, we're going to take 144, and you don't divide by 26, but you divide by the GCD of 26 with the size of the group. So now I have to do a little bit of math. 144 is 12 squared. So 4 times 3 squared. So what is it? 2 to the 4, 3 squared, something like that. And then 26, I can see it's 2 times 13. So apparently their GCD is 2, is the largest divisor that they have in common. So if you took 144 over 2, that would give you the number of, well, that's it, the number of elements that are in this cyclic subgroup, the number of distinct elements that are of, powers of x to the 26. That last one, the 72nd power of this, would give you 0 back, mod 144. So there's 72 items here. You can see now why you definitely don't want to start trying to write them out. You're going to be filling the whole page. All right, we are on the last problem. This one I only posted today, but I'll go ahead and do some of them. I'll do the whole thing, I suppose. So we're looking at 49. This is an analysis question. It's testing for convergence. And you're given a few different questions. So the first one, maybe I'll do 1 and 3, and then I'll give myself some space for the other one. So in 1, this is our series, but you can kind of see if you were to start adding these up, let's let Sn be the sum as n goes from 1 to capital N of our guys, you can see that like Sn is you get like root 2 minus root 1 plus root 3 minus root 2. So you get some sort of, you get some cancellation, right? You get plus root 2 minus root 2. You always get plus root n plus 1 minus root n, so it subtracts the previous. So on the next one we're going to get root 4 minus root 3, root 5, etc. If we stop at n, you'll have an n plus 1 here, but you'll have removed the previous term contribution, the positive contribution of root n. So all these cancel, the 3's cancel, the 2's cancel. The only ones that don't is this last term. Oh, did I skip the first term? I think I did. No, I didn't start at 0. I chose to start at 1 for some reason. Okay, that's fine. Anyway, you get this, or 1, you know, root n plus 1 minus 1. But the point is, does this have a limit? Well, no, the n's are getting larger and larger. So the limit of this partial series is infinity. So this is divergent. So 1 is divergent because the partial sums are growing larger and larger. They're growing like a root n as n gets big. Another pretty straightforward one in this list, I presume you've already looked at them and tried them if you're watching this video. This one's a root test, you know. An is the nth root of n minus 1, and then we take all this and we raise it to a power. So this is begging for you to take the nth root of it. The root test says if you can take the limit of the nth root, if it's less than 1, then you've got a convergent series. If it's greater than 1, it's divergent. And if it's equal to 1, you don't know, you just want to try a different test. So when we take the nth root, we're looking at the limit of the inside stuff, you know, the nth root of n minus 1. Unless you've done this before, this one's probably kind of up in the air at the moment. Say it's like 100 to the 1 over 100, or 1,000 to the 1 over 1,000, like the millionth root of 1 million. So it's a little unclear. It seems like it could be going to 1, but it is going to 1. You just need to, you could take a logarithm to show it. So let's let y be this chunk. We're going to split it up, do this limit minus this limit, but this limit is just 1. So split it up and look at this guy, and then take a logarithm of that, and you can pull this power down, and you can play with it, and it'll work out for you. So if you took log y, you'd get log of n to the 1 over n, right? So you can pull this power down. You're getting 1 over n times log n. You're getting log n over n. And now when you try to take the limit of that as n gets big, you're getting 0 over 0. So it's perfect form for some L'Hopital business. So this is the same as, by L'Hopital, the limit you would get, you know, if I took this limit, if I had put a limit here, like I should have, you get the same as the limit if you take the derivative on the top and the derivative of the bottom. Well, pretend n was a variable and take the derivative. You'd get the limit of 1 over n, and downstairs you just get a 1. And so now as n goes to infinity, you're getting 0. So we can see that log y goes to 0. Log y tends to 0. And if you take e raised to this, you'll have canceled that out. So y goes to e to the 0, or 1. So this part goes to 1, which means the whole thing goes to 0, which is less than 1. So what I was doing this whole time was I took a root test. I'm going to say this is convergent by a root test. And now, see if I have some paper I can use. So now I'm looking at 2 and 4. Let's do 4 first, I suppose. It doesn't, you know, it doesn't mention what that complex number z is or anything. It just says So obviously there are some for which this makes no sense. Like if you threw I in there for z, then every 4 terms you're going to get division by 0, so it doesn't even make any sense. You plug -1 in there, then half the time it doesn't make sense. So we're going to get different answers depending on what complex number you plug in. I guess I'll avoid the case on the unit circle. Because we can already see 2 examples off the top of my head where it's divergent on the circle. It's probably maybe I'll address it when I post a submission about the behavior on the circle. But first of all, if I would split this into 2 cases. If you take something within the circle, you'll get some kind of large behavior, right? If you take something small, then this gets big. In fact, this shrinks to 0, so you're getting something that tends to 1. So it definitely does not converge. It's going to be divergent. What is that, the divergence test? Basically, the terms don't go to 0. So the things you're adding, if they're of fixed size, or if they converge to something that's bigger than 0, then of course the sum is divergent. That's what I'm saying is going to happen in this case. So if we look at something like this, because this is less than right, then the reciprocal of it is bigger. But we also know that this is, because this was small, this is sort of tending towards 0. Does that make sense? This is less than 1. If you raise it to some power, it's still less than 1. So this is less than 2. Okay? So when you take the reciprocal, if we took the magnitude of A, the magnitude of AN is this, which is still this, right? Anyway, the reciprocal of this is greater than or equal to 1/2, is what I'm claiming. So your terms never get smaller than half. This is divergent in this case. But on the other case, the case where it's bigger than 1, you get sort of the opposite behavior. So here, that'll tell you that this is also bigger than 1. If you add 1 to it, wonder where I was going with this. Oh, I think I see. I was planning to think of this as, you know what you could do? You could compare it. Because, like, if this was bigger than 1, my instinct is this. Let R be 1/z, or something like that is what I'm saying. If z is bigger than 1, this is less than 1, and it's convergent. Because it's geometric, So that was my idea. You don't actually have that, but you have something even smaller than that. So our series is less than this series, which is finite. So the rest of that thought process is just that when you have something bigger than 1, when you raise it to a power, it's still bigger than 1. It's bigger. If you take 1 plus this, it's I suppose it's bigger than 2, right? So now when you take the reciprocal, well, that's actually, what I'm saying now is actually not enough to get convergence, so I shouldn't be talking about that anymore. I was just sort of thinking out loud. Yeah, I thought I could maybe compare it to like half as the ratio. So we could say that this is less than 1. But I guess I better be a little careful about that. Yeah, I think I'm going to leave that alone. But anyway, it is convergent because it's a geometric, by comparison, converges by comparison and with a geometric series. So you can see that these terms are smaller than those terms because they're bigger, like the denominator is bigger than that term. But this term, since z is larger than 1, that's geometric, effectively. It's absolutely convergent. So that's it for part 4. And then the one I was going to come back to is 2 here. Is a little tricksy. N plus 1 minus root n over n. So we saw at the beginning, if you just replace n here on the bottom with a 1, this is divergent because it's like telescoping. When you put an n there, that's a little different. So my first instinct when you write out terms, Sn now looks like, say, root 2 minus 1 over 1 plus root 3 minus root 2 over 2 plus root 4 minus root 3 over 3, etc., right? So they're no longer telescoping. These things don't actually cancel. My first instinct had been to show that it blows up, so I was like, oh, well, it's bigger than, I'll just take like one of these terms, like I'll fix the denominator and then I'll write down a bunch of terms. So suppose these were all 1/10 instead, then the first 10 terms are actually, the first 10 terms of the real series are bigger than, right? Because you're dividing by smaller numbers. So you could compare this to like 1/10 times the first 10 terms summed up. I mean, just the numerators. Then you get some cancellation and you can look at it. So you end up seeing something like Sn, I'm just showing you my thought process. This is not going to work out for us, but for instance, I was like, well, what if I replace all the denominators with like a 10th? First we do 1/10, and then we sum up the first 10 terms. then what you're going to be left with is, I guess you get up to root 9. Nope, I guess you get to root 11? Yeah, technically you get up to root 11 minus root 10. But let's stop short of that anyway. We'll get up to root 10 minus 1, for example. And then I could do like 1/100th of root 100 minus root 10. When, you know, all the telescoping is happening here because I forced them to have the same denominator. Anyway, you can see that it didn't quite work out for me. I was hoping to show that this worked out to be like a finite number. Well, the problem is that wouldn't prove anything, right? If I prove this is bigger than 2 or something, then great. So what? Is it finite or not? I was hoping to show that this blew up, but it didn't blow up. What's this? 10 over 1,000 is 100. So you're subtracting 1/100th, and over here you're adding 10/100ths. Yeah. So this was the wrong idea, but it's kind of the right concept. What you can do instead, though, is look at the squares. So like here I see there's going to be a 2. If we just summed, if we went basically the other direction, try to bound it from above by something. So instead of taking like a denominator from later on, take a denominator from earlier on, and that'll make it larger. So like if I replace all these with 2's, I can see that that series is bigger than, yep. Like if I make the denominator smaller everywhere, right? That'll be a large, those terms will be larger, and the series you're looking at will be smaller than what you're looking at. So we're going to do the same kind of concept, but we'll add up, say, the first 3 terms. So maybe I won't even divide for the first 3 terms. I'll just divide by 1. I'll take just the first 3 terms on their own, and we end on 2 minus 1, right? So for the first 3 terms, I'll just do 1 over 1 times this plus that in the numerators. And at the end, you'll get root 4 minus root 3 plus root 3 minus root 2 plus root 2 minus 1. So you end up with 2 minus 1. So this is just coming from the first 3 terms. And then I'm going to take the next 5 terms, the ones that start at, let's see, the first term is a root 5, and then minus root 4. So we're going to put a quarter here, I guess. I think the next term that you see has 1/4 as its coefficient, or, you know, the denominator is 4 on that next term. Right? And then the first term that gets subtracted is root 4. So we're subtracting 2. But if I take 5 terms, we'll be stopping on root 9. And it's a 3. And then after that, I'll take the next 7 terms. So you can see I'm basically stopping when there's a square. I'm going to add up the first 3 terms because we end on a 2, the square root of 4. Then I'm going to take the next 5. And your denominator on that next term will be a 9th. Because that's like the first term that you see in our thing. The first term is root 9 minus root 8. So I'm saying you can regroup it like this. Everything in the parentheses will be a 1, and so you're comparing our series to this series, 1 plus a quarter plus a ninth plus a 16th, etc., which is convergent. Usually called a p-series. This is p-value 2. Or it's convergent if you compare it to... You could use an integral test to prove it if you're not familiar with a p-series, but that is why it's convergent. So number 2, I'm going to say, is convergent by comparison with a p-series, but the comparison I'm talking about is a little bit complicated. You have to do some regrouping of the terms. So I'm saying we'll do 1 times these, and then the next term would have been a quarter of root 5 minus root 4. Root 6 minus root 5, root 7 minus root 6, root 8 minus root 7, okay? And then the 5th term that I'm including, the last one I'm including, is root 9 minus root 8. So that's why everything cancels except for root 3 and root 4. So you're left with 3 minus 2. And then you do it again for the next odd number of terms, the next 7 terms. You can see since this was a 9, the next term is going to be a 10, so its denominator would have been a 9. So I'll take that coefficient, and that's actually larger than all the other denominators that are following for those next 7 terms. So this is a major, this is a larger series than the one that we're looking at with this, with these bigger denominators in it. We're taking the smallest denominator. It's the one that comes first on the what is this, 3, 8, on basically the 9th term of the series. This is our denominator, and the numerators that I'm including look like root 10 minus root 9 plus root 11 minus root 10 up to I think we're going to include root 16, and we'll stop there, right? And so you're getting 4 minus 3. Everything else cancels because of this telescopic business. Root 10 cancels, root 11 cancels, root 15 cancels. And the next term will be the one that's root 17 minus root 16, right? Oh, did I? No, that's right, that's right. Root 18 minus root 17, etc. So all the ones that are non-powers get canceled, and we eventually hit on like root 25 minus root 24. Root 24 cancels. But anyway, this is apparently, what is it, 5, 7, 9. There must be 9 terms here. Yeah, that's right. Anyway, 9 terms there, and so the leading coefficient here, the denominator there must have been 16, and that's a smaller number than all of these other ones, and so its reciprocal is bigger than all the other ones. So a larger series would be one where you just put 1/16 in front of all these terms and added them up. But when you do that, of course, it cancels, and you're getting this sum that we just talked about, which is a convergent series. All right, ladies and germs, thank you for tuning in. I hope this was helpful. Have yourself a great day.